In a previous video, we have seen the derivation of the ideal gas equation of state from Boyle's law, Charles' law, and Avogadro's hypothesis or law. Okay, so the ideal gas equation of state tells you the relationship between properties of the gas such as pressure, volume, number of moles, and temperature. We now here see an application for this ideal gas equation that tells us about the molar volume of an ideal gas. The molar volume is simply defined as the volume occupied by 1 mole of an ideal gas at a given set of conditions of pressure and temperature. Okay, so the molar volume from the ideal gas equation of state can be derived simply as this. That is the volume occupied per mole. Okay? And it's equal to RT divided over the pressure. Right, so we can calculate then what the molar volume is for an ideal gas by agreeing to a set of temperature and pressure conditions. Okay, typical temperature and pressure conditions that are used are STP, for example. This means standard temperature and pressure conditions, and the definition is going to be the pressure is equal to 1 atmosphere, and then the temperature is going to be equal to 0 Celsius or 273.15 Kelvin. Right, so then let's calculate what the molar volume of an ideal gas is at STP conditions. We come to the ideal gas equation of state, and that R is equal to 0.08206 atmosphere liter over mole Kelvin. Okay, then we have to multiply by the temperature, which is in Kelvin, because that is forced by this use of R in Kelvin. So that is 273.15. And then divide over the pressure, which is 1 atmosphere. This number is exact, so you have there an infinite number of significant figures. Okay, when we calculate that, it turns out that the total, the molar volume of an ideal gas at STP conditions is equal to 22.4 liters per mole. Or for every mole of gas that you have, the volume occupied is 22.4 liters. Okay, that volume is equal to a cubic box of 11 inches by 11 inches by 11 inches. Okay, so a box of approximately this size that contains exactly 1 mole of an ideal gas, or an Avogadro number of gas particles. Now, something that is very interesting about this ideal gas molar volume is that it's completely not connected to the nature of the gas, right? So if you have that oxygen or nitrogen or argon behave as an ideal gas, it turns out that all of them would occupy, or 1 mole of each one of them would occupy exactly the same volume, right? So the molar volume does not depend on the nature of the gas. And again, that only happens for ideal gases. Right, so under what conditions do we have ideal gas behavior? Well, under these conditions where you have reasonably low pressure and low temperatures, most gases, regardless of what their nature is, behave as an ideal gas to a really good approximation. The ideal gas formalism breaks down once you start to have really high pressures, right? So for pressures that are perhaps 100 to 200 times greater than 1 atm, then you would start to see that this equation actually does not work out very well. What that means is that under conditions that are normal to us, conditions that we regularly work in the laboratory, the ideal gas approximation is actually quite good. To close up this video, we're going to recalculate this at a slightly different set of temperature and pressure conditions, which is called SATP. Okay? SATP means standard ambient temperature and pressure conditions, which are slightly different from here. The pressure will be 1 bar exactly, and the temperature is going to be ambient temperature, which is 25 Celsius or 298.15 Kelvin. Okay, so here we actually, because we're going to be using this R that forces you to use atmospheres as the unit of pressure, we actually have to figure out how much 1 bar of pressure is in ATM, and they happen to be only different by about 1%. Okay, 1 bar is equal to 1.01325 ATMs, and that conversion will be provided to you. Okay, so we come to this expression, and now we calculate the molar volume at SATP. Right, so we have to just change the temperature and pressure. That would be 298.15 Kelvin And then we'll have the pressure would be 101,325 atm. Okay, so the main change between STP and SATP would be in temperature. Right? You increase by 25 degrees, the change in the pressure is very, very minor, it's only about 1%. Okay, so what you expect is that if you increase the temperature, then the molar volume should go up. Right? And we know this from Charles' law that tells you the relationship between volume and temperature when you have constant pressure and constant number of moles. Anyway, so when you actually carry the calculation, that number happens to be 24.1 liters per mole. Okay, which again is slightly larger than what you have at STP. Okay, and again, it's exactly the same for every gas regardless of its nature.